Dear colleagues, the lesson of today is dedicated to the behavior of an air compressor. Our task is to understand what electrical power depends upon and which parameters are to be changed for efficiency optimization. The compressor we are going to see are of two types, the centrifugal and the screw ones. We also will understand the difference between oil-free and lubricated ones, and eventually we come to two different formulas, and by playing with the inputs we explore the effects on the overall power demand. I hope you will enjoy it. Let's see.
The air compressor is a machine to produce airflow at a higher pressure than atmospheric. There are different technologies to achieve it. That means different type of compression methods. In our industrial application, we are dealing mainly with two, the centrifugal and the screw compressors. Since the compression process is generating heat, the heat must be taken out with air or with water. The centrifugal machines are mostly water-cooled. On top, the screw compressors can be lubricated or not. The lubrication offers an advantage that we will see later on. We represent here briefly the schematic process of the two by Conti most used machines, the centrifugal water-cooled on the left side and the lubricated air-cooled screw on the right side. The centrifugal consists of three stages. Each stage is made by an impeller and a heat exchanger. Here is the impeller and here is the heat exchanger. The air enters in sequence in the first, then the second and then the third one. Finally, it leaves the machine here. By the intake, there is also a filter and a throttling valve. The impeller has different size and different speed, being the speed higher than the motor, and there is a gearbox in between. The gearbox is lubricated by oil, but the oil is not getting in touch with the air stream. The screw machine consists in a couple of screws which are turning together and opposite. After the compression, the air is filtered and the oil is flowing back, first into an heat exchanger, it's cooled down and then comes back to the screw housing. Differently from the centrifugal, the oil screw machine is only one stage and the air stream is mixed together with oil. There are existing also water lubricated screws as well as non-lubricated ones. Let's start from the centrifugal machine and from the thermodynamics. The first principle says the enthalpy is the sum of the heat and the work. If the transformation is adiabatic, like the compressor within a centrifugal machine, then the heat Q is zero. The work is equal to the enthalpy difference, hence the expression above. Moreover, using the isentropic equation of the perfect gases, we come to an expression linking temperature and pressure, being K the ratio between the two calorific values at constant pressure and constant volume. By plugging this formula into the first one, we come to this relation for the specific work. This is the isentropic work. Adiabatic, yes, but still ideal. Actually, during the compression, the entropy increases, so our delivery temperature T2 is something higher, like in the chart. To consider it, we introduce the polytropic efficiency eta, and we write the work in this form. What we have seen is valid for one stage. What happens if there are many? The overall compression ratio is equally distributed among the stages, and after each one, the air is cooled back, theoretically till to the entry condition. In the picture, we represent three stages machine. The formula at the previous page is changing by adding n, which is the quantity of stages, both as a multiplication factor and as a denominator of the power beside the polytropic efficiency. The result is that the work decreases the more are the stages. If the stages are infinite, we get the formula of the isothermal work, and this is the minimum compression work under given conditions. The isothermal efficiency describes how the compressor performance is close to it. We have spoken till now about work and not power yet. What is missing? The mass flow rate. This mass flow we can express as volumetric flow times the density. Now we are dealing with a compressible flow. The density is changing. Which shall we take as reference? By using the standard ISO 1217, the reference conditions are 20 degrees and 100 kilopascal. So we can write the mass flow as a volumetric flow at standard condition, divided by a constant 3048. We remember that the mass flow in this case is kilogram per second, while the volumetric flow rate is cubic meter per hour. If we combine the expression of the flow rate and the one of the work, we get the power. If we include both the mechanical and electrical efficiency, we come to the final expression of the power needed by the electric motor. At the right side, we have the legend what each input is representing. The parameters depending upon the compressor are the stages N and the three efficiencies. Important is that such a formula we can use for any unlubricated machine. Centrifugal, screw, piston, either water or air cooled. This is the mechanical efficiency, the electrical efficiency, the polytropic efficiency, and the number of stages. The screw lubricated machine must be treated separately. Starting from the first law of the thermodynamics, we recognize that both heat and work are present. We cannot consider the transformation adiabatic because during the compression the air is getting cooled by the oil. This happens inside of the screw, while with the centrifugal machine was different. The air was cooled outside of the impeller when the compression phase is terminated. Here we must introduce another type of transformation, the polytropic one. The equation is similar to the isentropic, but the coefficient m is a number between 1 and k. And we come to this expression for the power, which is formally similar to the one we have seen, but in place of epsilon we have alpha, which is m minus 1 divided by m, and then the number of stages is only 1, because those machines are mostly single stage. And moreover, the polytropic efficiency disappears because transformation is already polytropic. Instead, we have another efficiency, the lubrication efficiency eta L, and this takes into consideration the power lost due to the friction of the oil, the volumetric efficiency of the screw, and the power of the auxiliary fan. And both M and eta L must be experimentally found. This is the polytropic transformation. Now we run an example taken from a real case. The centrifugal compressor was completely overhauled and its performance measured in a testing facility by the vendor. Let's input all the parameters in the formula. The flow rate is given, 3 stages, efficiency and boundary condition for the air are also known, and the result says 643 kilowatt, which is consistent with the metered power. In this formula, we do not consider the effect of humidity for making the calculation easier, but in the real case it is considered. Why we have made all this long exercise? In order to understand what is affecting the power demand and how to optimize it. Should we need to reduce the energy consumption of the machine, what we can do? Let's speak about the machine itself, not about its regulation. For the time, we assume it works fully loaded. By only adjustments, we can reduce, for instance, the delivery pressure, supposing that our process is not suffering from it. By dropping 1 bar, we gain about 7%. And by using chilled water, supposing that it is already available, we can gain further 20 kilowatt, altogether 10%. Should we have at disposal a higher budget, we can consider a machine overhauling. For instance, we can increase the polytropic efficiency by replacing the impeller with a new profile, and we get another 4%. And by using a high efficient motor, we come to 16% of power saving. That is about 110,000 euro of power saving, with a payback of less than 1 year if we consider the cost for the machine overhauling. Now we make another example for the screw compressor. Here the parameters are a little bit different. Beside the flow rate, we know the polytropic coefficient M, also alpha is calculated. The mechanical, electrical and lubricating efficiency is also given. And also we know the ambient conditions in terms of temperature and pressure. And so we get for the power 265 kilowatt, very close to the value metered at the test facility, 261 kilowatt. We place now the same question as per the centrifugal one. What we can change to increase efficiency? By reducing the delivery pressure of 1 bar, we can save also something about 7%. And since the cooling is by air, we can make the air colder, dropping from 30 to 20 degrees by using an exchanger up front. Both together may achieve a saving of 11%. To go further, we need to increase the lubrication efficiency, for example by adopting a different oil with less friction losses or a high efficient fan. Again, a high efficient motor can bring a further effort. Save altogether about 17%, and then we need to run a case study to see if the investment is worthy or not. I want to spend a couple of words how we can judge if a compressor is good or not. Normally, we refer to the specific consumption, kilowatt-hour per cubic meter, and we say the less is the better. But this is actually not true. It would be true if we compare machines with same boundary conditions, inlet temperature and pressure, delivery pressure. Let's look at the table. The first and second row is our centrifugal machine. In the third and fourth, our screw one. If they are working under similar condition, that is 8.5 bar, the specific consumption is better for the centrifugal one. 89 is less than 104. But if we change now the delivery pressure into 10 bar and 7 bar respectively, we notice that the specific consumption of the second is better. 92 is less than 97. Nevertheless, if we refer to the isothermal efficiency at the right column, the first machine is still better. The isothermal is not much affected by the boundary conditions, and the second machine is always lower. It means the isothermal efficiency is the right parameter to assess if the machine is good or not.
Till now, we have seen only the performance of a single machine, not its behavior within the compressor room. We do not speak about regulation at all. This topic will be treated in a dedicated video, however. I hope to have told you something new. Maybe you are already familiar with compressors, but this is from another perspective. See you again.